The expansion of high-speed rail networks has become a cornerstone of modern transportation infrastructure, requiring unparalleled precision, advanced engineering methodologies, and continuous technological advancements. High-speed rail systems demand a high level of track accuracy to support the dynamic loads and operational speeds associated with modern railway transportation. Any deviation in track alignment, installation errors, or structural deficiencies can lead to performance degradation, increased maintenance costs, and safety concerns. Since 2006, TECSA has been at the forefront of high-speed railway track mounting, pioneering innovative installation methods that have redefined industry standards. By integrating cutting-edge mechanized mounting solutions, TECSA has eliminated inefficiencies associated with traditional track installation methods, significantly improving construction timelines, track durability, and overall cost-effectiveness. TECSA has introduced a highly specialized railway mounting process, the TECSA system, which has revolutionized track installation by eliminating the need for an auxiliary track, a conventional requirement that traditionally increases material consumption, project duration, and labor demands. Instead, TECSA system employs two distinct track mounting methodologies that streamline the rail placement process. The first method utilizes an unloading track gate system, allowing for the direct placement of long welded rail sections onto the railway sleepers, ensuring optimal alignment and load distribution. The second method leverages a lateral unloading mechanism, facilitating the parallel installation of track components with increased precision and speed. These methods collectively enhance the continuity of track assembly, reducing unnecessary intermediate steps while maintaining structural cohesion and geometric accuracy. The installation workflow of the TECSA system follows a structured sequence of highly specialized procedures, ensuring that each phase contributes to track stability and alignment compliance. The process commences with topographical survey and data collection, where geospatial mapping technologies are utilized to assess the terrain, establish reference points, and define the optimal track alignment. This stage ensures that the track installation adheres to railway engineering specifications, minimizing the risk of misalignment or foundation irregularities. Following the survey, the distribution of railway sleepers is conducted along the predefined track alignment, preparing the foundation for precise rail placement. The final preparatory phase involves the stabilization of the track foundation, ensuring that the underlying structure can support the mechanical loads exerted by high-speed railway operations. Unlike conventional railway mounting systems that rely on auxiliary tracks constructed from second-hand materials, such as wooden sleepers and lightweight rail profiles, the TECSA system eliminates this requirement entirely. The auxiliary track method, commonly used in traditional installations, has become increasingly cost-prohibitive and logistically challenging due to the scarcity of reusable track components. By bypassing the need for auxiliary tracks, the TECSA system allows for direct track mounting, significantly improving both installation efficiency and cost optimization. The elimination of auxiliary tracks translates into substantial efficiency gains across different phases of track mounting. In leading track installations, TECSA's approach doubles the productivity compared to traditional methods. Meanwhile, in parallel track installations, the efficiency is quadrupled, allowing for the simultaneous placement of rail sections with minimal downtime. This innovative track assembly model not only accelerates project delivery, but also enhances the mechanical integrity of the railway infrastructure, ensuring that tracks exhibit higher resistance to mechanical stresses, temperature fluctuations, and long-term operational wear. TECSA has successfully implemented its revolutionary track mounting system across major high-speed railway corridors, demonstrating its effectiveness in large-scale infrastructure projects. The TECSA system has been deployed in the Madrid-Zaragoza-Barcelona French border high-speed rail network, where its ability to facilitate rapid and accurate track placement has played a crucial role in expanding Spain's high-speed rail infrastructure. Additionally, TECSA's mounting technology has been used in the railway access routes to the northern and northwestern regions of Spain, reinforcing the structural efficiency of new rail connections. Another notable deployment of the TECSA system includes its application in the Madrid-Castilla-La Mancha-Valencia high-speed railway, where its second-generation lateral unloading methodology was introduced to FERT. The Stobart, Alderley Edge Railway was conceived as a strategic transportation link to enhance connectivity between key industrial hubs and residential communities in the northwest of England. The project was initiated by Stobart Rail, a major infrastructure and logistics firm, in collaboration with local councils, railway authorities, and private investors. The need for the railway arose from increasing congestion on road networks and the growing demand for efficient freight and passenger transport. Initial feasibility studies conducted in the early stages assessed potential routes, environmental impact, and financial viability. These studies determined that a railway linking Alderley Edge with existing major railway lines would be a cost-effective and sustainable alternative to road transport. Following extensive public consultations and regulatory approvals, the project was greenlit with an estimated budget covering land acquisition, construction, and operational setup. Engineers, urban planners, and transport specialists worked together to finalize the optimal railway alignment, considering factors such as topography, existing infrastructure, and ecological preservation. Once the route was determined, preliminary ground surveys and geotechnical investigations were conducted to ensure that the land could support railway infrastructure, including tracks, bridges, and tunnels where necessary. Engineering challenges and solutions. One of the most significant challenges faced during the construction of the Stobart, Alderley Edge Railway, was the varied terrain of the region. The railway needed to navigate through a mixture of urban areas, farmland, and hilly landscapes, requiring precise engineering solutions. To accommodate changes in elevation and avoid excessive gradients that would make train operations inefficient, a combination of cuttings, embankments, and tunnels was employed. The construction team utilized advanced surveying techniques, including lidar scanning and ground-penetrating radar, to assess subsurface conditions and identify the best possible alignments. In areas where soft soil or unstable ground conditions were present, soil stabilization methods were applied, including the use of deep foundation piles and geotextile reinforcement. Additionally, several water bodies and natural habitats required careful planning to ensure minimal environmental disruption. Bridges and viaducts were strategically placed to allow safe passage over rivers and streams, while minimizing impact on local wildlife. Noise and vibration control measures were also implemented to mitigate disturbances to nearby residential areas, including the installation of sound barriers and track dampers. Construction phases. The construction of the Stobart, Alderley Edge Railway was divided into multiple carefully planned phases to ensure efficiency, structural integrity, and adherence to safety regulations. Given the complexity of the project, engineers and planners devised a systematic approach to minimize disruptions while maintaining a steady construction pace. The first phase focused on land preparation, including clearance of vegetation, relocation of utilities, and ensuring proper drainage systems to mitigate water accumulation in excavation sites. Special attention was given to archaeological assessments to document and preserve any historical findings before proceeding with large-scale groundwork. Additionally, temporary access roads were established for the seamless transportation of heavy machinery, materials, and workforce. Following site clearance, earthworks commenced, involving significant excavation, grading, and compaction of the terrain to create a stable foundation. Embankments were constructed in areas with low-lying land to elevate the railway to an appropriate level, while deep cuttings were made through hilly regions to maintain a gradual incline suitable for train operations. To reinforce stability, geosynthetics and soil compaction techniques were employed, preventing subsidence and ensuring long-term durability. The next phase entailed trackbed preparation, where a layer of crushed stone ballast was meticulously spread along the railway alignment. The ballast provided essential support, distributing the load from the railway sleepers and rails, while facilitating effective drainage to prevent water retention. Precision leveling and compacting of the ballast ensured a firm base before track laying commenced. Modern track-laying machinery played a crucial role in expediting the installation of rails, sleepers, and fasteners. Pre-assembled track panels were transported to the site via specialized rail transport vehicles, reducing the need for extensive on-site assembly. These panels were then methodically positioned and secured, ensuring precise alignment to meet railway gauge standards. The railway also required the construction of multiple stations and depots, designed to accommodate both passenger and freight operations. Each station was equipped with modern amenities, such as digital ticketing systems, automated entry gates, well-lit waiting areas, and accessibility features for passengers with reduced mobility. Freight depots were strategically located to facilitate efficient loading and unloading of goods, incorporating high-capacity storage areas, overhead cranes, and container handling equipment. Beyond track and station construction, attention was given to integrating robust signaling and safety systems to enhance operational efficiency and prevent potential hazards. Advanced signaling technology, including electronic interlocking systems and centralized traffic control, was installed to enable seamless communication between train operators and control centers. Automated level crossings, equipped with sensors and barriers, were implemented at road intersections to ensure public safety. A dedicated electrification phase was introduced for sections requiring electric-powered trains. Overhead catenary systems were installed, supported by precisely positioned masts and tensioning mechanisms. The electrification process involved extensive testing to ensure voltage stability, insulation integrity, and uninterrupted power supply for locomotive operations. Final construction efforts included the establishment of maintenance facilities, emergency response units, and auxiliary structures such as pedestrian overpasses, noise mitigation walls, and weather protection canopies at stations. Landscaping and environmental restoration measures were also undertaken, incorporating green spaces, tree replanting, and habitat preservation programs to offset the impact of railway development. As the physical construction reached completion, the railway underwent an extensive testing and commissioning phase. Trial runs were conducted with empty and loaded train carriages to evaluate track integrity, braking efficiency, and traction performance under varying conditions. Data from these trials was analyzed to fine-tune operational parameters and address any potential mechanical issues before full-scale launch. Stringent safety inspections were carried out by regulatory authorities to verify compliance with industry standards and legal requirements. Emergency preparedness exercises, including fire response drills, derailment simulations, and evacuation procedures, were conducted to ensure that railway personnel were well equipped to handle unexpected situations. Impact and future prospects. The successful completion of the Stobart, Alderley Edge Railway significantly improved regional transportation, providing a reliable alternative to road transport and reducing traffic congestion. It facilitated faster and more efficient movement of goods, benefiting industries that relied on just-in-time delivery systems. Additionally, the railway enhanced commuter convenience by offering a sustainable and cost-effective mode of transport for residents traveling between Alderley Edge and other key locations. Environmental benefits included reduced carbon emissions due to decreased reliance on road freight and private vehicle usage. The project also contributed to economic growth by creating job opportunities during construction and ongoing railway operations. Future expansion plans are being considered to extend the railway's reach, integrate additional stations, and incorporate emerging rail technologies, such as hydrogen-powered trains, for further sustainability improvements. Overall, the Stobart, Alderley Edge Railway stands as a testament to innovative engineering, strategic planning, and collaboration between public and private entities in advancing transportation infrastructure for long-term regional development. The Calder Viaduct is a crucial railway structure, providing a key transportation link over the River Calder. Maintaining the integrity and functionality of the viaduct is essential to ensure safe and efficient railway operations. In a recent infrastructure upgrade, the steel deck of the viaduct was replaced with a modern glass-reinforced plastic GRP deck. This transition was necessary to address structural concerns, reduce maintenance requirements, and extend the service life of the viaduct. The project showcased the latest advancements in composite materials, innovative engineering solutions, and meticulous planning to achieve a seamless transition with minimal disruption to railway operations. The refurbishment of the Calder Viaduct involved the removal of the aging steel deck, which had suffered from corrosion and fatigue due to prolonged exposure to environmental elements. The replacement process followed a structured approach known as track-off, track-on, ensuring minimal disruption to railway services. This method required the temporary removal of the railway track, installation of the new GRP deck, and reinstallation of the track in a carefully coordinated sequence. Extensive pre-planning ensured that the operation was executed efficiently, with the new deck offering improved resilience and lower life cycle costs compared to the previous steel structure. The decision to replace the steel deck with a GRP deck was driven by several engineering and economic factors. Unlike steel, GRP is highly resistant to corrosion, making it ideal for structures exposed to moisture and fluctuating temperatures. GRP is significantly lighter than steel, reducing the overall load on the viaduct's supporting structure and minimizing stress on foundation elements. The composite material offers a longer lifespan with minimal degradation over time, particularly in environments with high humidity and temperature variations. The non-metallic composition of GRP eliminates the need for frequent repainting, rust treatment, and anti-corrosion coatings, resulting in lower long-term maintenance costs. Prefabricated GRP panels enable faster installation compared to traditional steel decks, minimizing railway downtime and improving project efficiency. The use of composite materials contributes to environmental sustainability by reducing material waste and carbon emissions associated with steel manufacturing and maintenance processes. Project execution. The project commenced with an extensive planning phase that involved engineers conducted a thorough assessment of the viaduct's existing framework to ensure compatibility with the new deck material. Advanced structural simulations and stress tests were carried out to predict load distributions and performance under operational conditions. High-quality GRP panels were fabricated off-site to precise specifications, ensuring seamless integration upon installation. The panels were subjected to rigorous quality checks, including strength testing and fatigue analysis. Arrangements were made for the transport of materials, workforce deployment, and scheduling of railway closures to facilitate smooth execution. Contingency measures were put in place to mitigate potential delays due to adverse weather or unforeseen circumstances. The railway track was carefully dismantled, including the removal of ballast, sleepers, and fastening components. Specialized machinery was used to lift and store track components for reinstallation. Using specialized lifting equipment and cranes, the deteriorated steel panels were extracted from the viaduct, taking precautions to prevent damage to the underlying structure. Workers operated within tight safety protocols to ensure efficiency and prevent hazards. The prefabricated GRP panels were lifted into place and securely fastened to the viaduct's framework using advanced fixing techniques. The lightweight nature of GRP expedited this process, reducing installation time and minimizing stress on the existing structure. Once the new deck was in position, railway tracks were reinstalled, ensuring precise alignment for optimal train operations. High-precision laser measurement tools were employed to verify track geometry and alignment. The refurbished viaduct underwent rigorous testing to verify structural integrity, including dynamic load assessments, stress analysis, and safety inspections. Trial runs were conducted using different train loads to confirm operational efficiency and stability. After confirming compliance with railway standards and regulatory guidelines, the viaduct was reopened for operation. Documentation and post-installation monitoring protocols were established to track performance and detect any potential issues in the early stages.